Hello students, now we are going to discuss the topic that is Valence Bond Theory of Complex. It is a very important topic to know about the shape of the complex, the magnetic nature of complex, and the nature of ligands, the nature of metal ions, how the complex, the shape of the complex differ from one another, how the magnetic character of the complex differ from one another by changing different ligands. So today we will discuss these things. This Valence Bond theory was first studied by L. Pauling. He mainly compared the nature of different complex on the basis of their shape and magnetic character. According to this, the first feature is the central atom and ion makes available the required number of empty orbitals. We know the complex is made of metal atom or ions and ligands. So there is a interaction, there is a overlap between the orbitals of metal atom and the orbitals of ligand. So how many number of ligands required to form bond with the particular atom or ions depends upon the availability of number of empty orbitals in the metal atom. The empty orbitals of metal atom or ion intermix, forming the required number of hybrid orbitals. So, empty orbitals of metal atom or ion intermix, forming the required number of hybrid orbitals. So, in the second step, what happens? That empty orbitals available for the overlapping, for overlapping with the ligands orbitals, that required number of empty orbitals of metal atom intermix, forming hybrid orbitals. So before overlapping, the orbitals must intermix one another, forming hybrid orbitals. That you know the concept of hybridizations. Then empty hybrid orbitals that produce overlap with orbitals of lone pair containing orbitals of ligand containing lone pair of electrons, forming dative bonds. So always the bond between ligands and metal atom is dative bond, already we have discussed. So this overlapping forming a dative bond. During overlapping, the particularly d orbital which are involved in the formation of hybridization may either inner or outer orbital take part. Either inner or outer. Inner means n-1d, inner means you can write n-1d, and outer means nd. This either inner or outer d orbital take part in the hybridizations. So on that basis, if inner orbital is taking part, that complex is called what? Inner orbital complex. If outer is taking part, outer orbital is taking part, that is called outer orbital complex. But generally, inner orbital complex are called low spin complex. Low spin complex means number of unpaired electrons are less. And outer orbital complex are called high spin complex. The number of unpaired electrons is more. Then the magnetic nature of the complex depends upon number of unpaired electrons available in the atom or ions. If there is no unpaired electrons, this is called diamagnetic. That is called diamagnetic. If unpaired electron is available, that is called paramagnetic. Already know this concept. Having unpaired electrons, paramagnetic. Having no unpaired electron, that is diamagnetic. So magnetic character can be known, the availability of unpaired electrons. And the shape of the complex, it depends upon the hybridization of the metal atom. Generally, what type of hybridization it produces, and the shape, it may be octahedral, it may be tetrahedral, it may be square planar. But generally, this concept we have to know. sp3 means tetrahedral, and dsp2 means square planar, and d2sp3, that is octahedral, and sp3d2, that is also octahedral. This is the very important concept of valence bond theory. If sp3, that is tetrahedral, if dsp2, that is square planar, if d2sp3 means inner, d is inner, d2sp3, that is octahedral, and sp3d2, that is also octahedral. But the nature of magnetic character will differ, but the shape will be same for both. Only they differ in magnetic character. Here also they differ in magnetic character, and also they differ in shape. sp3 is always tetrahedral. So now let us discuss some examples of that inner orbital complex and outer orbital complex, which is low spin, which is high spin complex. We'll start from octahedral complex. Let's start octahedral complex. In octahedral complex, it depends upon the ligands used. Suppose we take cobalt F6 whole bracket 3 minus. This complex, you have to assume there is no specific rule that why this complex is inner orbital complex, why this complex is outer orbital complex. There is no specific rules for knowing this inner and outer, but generally it depends upon the nature of ligands. We will discuss the nature of types of ligands on the basis of their nature in the next, that is crystal field theory. But valence bond theory, only it is one assumption that for this type of complex the hybridization is this. So COF6, that complex, its hybridization is your sp3d2, and shape is octahedral. Shape is sp3d2 means octahedral. Height and weight, we know cobalt charge is here 3. Here cobalt charge is 3. So cobalt plus 3, if you write, the cobalt plus 3 configuration is argon 18, then cobalt is 3d7 4s2. Here 3 electrons are already lost. So 3d7 4s2 will be how much? 3d6 4s0 and 4p0 and 4d0, all are 0, because cobalt is 27. Now it is instead of 27 already 3 electron is lost, that is 24, and 24 means it will be 37 4s2, then 3 electron lost, 2 from S and 1 from D, that's what is 3d6 4s0 4p0 4d0. Why I am writing this 4s 4pt? Because the config, that the hybridization is sp3d2, so sp3d both will take part. So what you can write? D here remains same, no involvement of D, 5d, then 1s, then 3p, then 5d, 4d. So this is your 3d, this is 4s, this is 4p, this is 4d, and here you see how many electrons in D? 6. 1, 2, 3, 4, 5, 6. Then S, P, D all are vacant, because vacant orbitals required for accommodation of lone pair from ligands. So as it is 6 ligands, so 6 vacant orbital requires 1, 2, 3, 4, 5, 6 up to this. So hybridization is hybridization is sp3d2, and forming how many hybrid orbitals already know? Forming 6 hybrid orbitals, because 6 atomic orbitals intermixing, forming 6 hybrid orbitals. These 6 hybrid orbitals are vacant, and these vacant orbital overlap with the lone pair, with the orbitals of the ligands. With the ligands. And here ligands is, what are the ligands? Ligands are F minus. So you can write here F minus, F minus, F minus, F minus, here F minus. So F minus, orbital of F minus having lone pair overlap with sp3d2 hybrid orbital forming a dative bond. So the structure of that this complex is, this is your cobalt octahedral complex. This is here 6 fluorine will be like this. Okay, then as this complex is carrying 3 minus as per the formula, and this is octahedral complex. It is a octahedral complex, and magnetic character, if you see how many unpaired electron elements, 1, 2, 3, 4, 4 unpaired, so paramagnetic. It is paramagnetic. And magnetic moment can be calculated. You know the formula, a mu is equal to n into n plus 2 square root. Here n is 4, 1, 2, 3, 4. So that is 4 into 4 plus 2 square root. That is how much? That is 24. 24 square root. Bohr magneton, Bm. This is the unit of mu value. Magnetic moment is Bm. So 24 square root, that is this much of Bm, that is magnetic moment of this complex. So it is a octahedral complex, paramagnetic character, and sp3d2 hybridization, that is outer orbital complex. D2 means outer orbital complex, and it is also called, as unpaired electrons are available, that's why it is called high spin complex. This is also called high spin complex. Let us take another octahedral complex having inner orbital complex, that is having inner d orbital take part. That depends upon, suppose CO, you take NH3 whole 6. This complex, this is 1, 2. This complex, if you write here, the cobalt same, cobalt is 3 plus, 3 plus means as per the configuration, that 3d6, 4s0, 4p0. Here d is not required because for ammonia it is inner orbital complex. For fluoride it is outer orbital complex. So the d configuration is like this: 1, 2, 3, 4, 5, then S, then P3. So this is your 3D, this is 4S, this is 4P. Here D is not, 4D will not be used because 4D for only outer. As inner, it is a inner orbital complex. Inner orbital complex means your inner d orbital take part. Here 2d and sp3 all. So d to sp3, that is 6 will take part, and both these orbital overlap with ammonia. With ammonia, 6 ammonia. As for the formula, 6 ammonia are bonded, you are forming bonding with ammonia, forming complex. So here if you see here D6 means D6 will be filled in 3 d orbital. So you each carry 2 electrons. So this is the 6 electron of D, inner D, and the remaining 2d take part in hybridization, and this d and S and 3p forming 6d to sp3, and this vacant d orbital of 6d to sp3 overlap with the lone pair of ammonia forming dative bond. So remaining, as it has no unpaired, so it is diamagnetic. diamagnetic and shape is octahedral. Same shape like your previous cobalt. Here ammonia, 6 ammonia. And this whole complex carries 3 plus charge, but previously the whole complex carries 3 minus charge. So hexammine cobalt 3 complex is a inner orbital complex. It is a inner orbital complex. Inner orbital complex. And inner orbital complex means low spin. It is also called low spin. Low spin complex having no unpaired electrons, or that is unpaired electron is less, but here there is no unpaired electron. But here having 4 unpaired, that's a high spin complex. So you have to remember, inner means that is low spin and outer means high spin complex. So this is regarding 2 types of octahedral complex. One is outer, another is inner. Similarly, we will discuss octahedral, that is tetrahedral and square planar. Okay. Let us take another 2 hybridization, that is tetrahedral and square planar complex. Why we have taken both together? Because tetrahedral require 4 ligands and square planar also required 4 ligands. But what is the difference? Only difference in nature of ligands. So, for example, if you take NiCN whole 4 2 minus, this complex is the example of square planar complex. And here hybridization is DsP2. DsP2. How you can explain? You know, here the charge of nickel is 2. If you calculate the oxidation number, nickel oxidation number will be 2. So nickel it can be written as Ni plus 2. Nickel plus 2 is that we can write 3D84S0 because it is that is written as argon 18 3D8 4S0 and 4P0. Because from 2 electron from 4s is removed, that's why it is nickel plus 2. So which orbital take part in hybridization? 1d and 1s and 2p. So 1d, 5d, 1s and 3p. P has 3 orbitals, that's why 3. Then what happens here? D can be written as, first you will write like this, as it is a DsP2, you write first DsP2. This is 3D, this is your 4, this is your 4s, this is your 4p. So what happens? This is your 1d, 1s, 2p. So DsP2 forming 4 hybrid orbitals. 1d, 1s, 2p forming 4 hybrid orbitals, and the remaining how your 8 electron. 8 electron in 4 orbitals, each carry 2 electrons. Okay, so this vacant space is occupied by lone pair given by ligand Cn minus. So it is a Cn minus, Cn minus, Cn minus, Cn minus. Both are giving lone pair to vacant orbital. Vacant, which vacant orbital? Hybrid orbital. These hybrid orbital, 4 hybrid orbitals are vacant. Another hybrid orbital also vacant, but these 4 vacant d orbitals, 4 vacant hybrid orbitals take part in overlapping with the lone pair of orbitals containing lone pair of Cn minus and forming 4 what? Dating bond. So as it has no unpaired electrons, so it is diamagnetic. It is diamagnetic, no unpaired electrons, and is square planar complex. It is a square planar complex and shape will be like this. nickel at the center. So this is your Cn minus, Cn, having 2 minus charge and nickel carry 2 charge. Okay, this is square planar. Shape is square planar and diamagnetic. And hybridization is DsP2. If you take another complex of nickel, that NiCl4 whole bracket 2 minus, same, but only difference in ligand. When the differ in ligand, then the nature of hybridization will be changed. So here hybridization is, that is tetrahedral complex, and hybridization is sp3. It is not DsP2, it is sp3 because it depends upon chlorine ligands. So same, nickel charge is plus 2 here, nickel plus 2, that is your 3d8, 4s0 and 4p0. Then what will the hybridization here? Here D will not take part, then all D will be like this, 1s, 3p, then hybridization is sp3. So sp3 means 4, sp3 means 4 heavy orbital produced. So then d8, 1 2 3 4 5 6 7 8. Okay, then it is your 3d, it is your 4s, it is your 4p, and forming hybrid orbital 4 by intermixing s and 3p, and these vacant orbitals overlap with orbitals of ligand. Here ligand is Cl minus. So Cl minus, Cl minus, Cl minus, Cl minus, forming 4 dative bonds, and the shape will be, the shape orbital will be tetrahedral. Tetrahedral means you can draw like this, nickel 1 like this. This is your Cl, this is your Cl, whole carry 2 minus charge, NiCl4 whole 2 minus, and as it has how many unpaired? 2 unpaired, so paramagnetic. Paramagnetic and shape is tetrahedral. You see the difference between tetracyanonickelate and tetrachloridonickelate. Only differing ligands, the nature of hybridization changes and shape also changes. That is, here is tetrahedral, here is square planar. Magnetic character is paramagnetic, here no unpaired electrons, that's a diamagnetic. So the shape of the orbital, the magnetic character also depends upon the nature of ligands. It also depends on nature of metal ion, and here that we discuss which orbital is inner, which orbital is outer, which orbital is tetrahedral, which complex is tetrahedral, which complex tetrahedral, which complex will be square planar. It depends on the what? Nature of ligand. I will give some examples. You write down. You have to practice more. That chromium, ammonia, 6 ammonia, this charge, it is DS, it is your D2sp3 inner orbitals. Okay, iron, Fe, F6 whole bracket 3 minus, that is your sp3 D2. So many examples are there. So chromium complex like this. So it depends upon if you take your cobalt En whole 3. This is your inner orbitals, that is D2sp3. So in Valence Bond theory, the nature of hybridization of the complex depends upon the ligands used. So we have to remember that which complex has which type of hybridization. because it has no clear-cut idea from the Valence Bond theory that which complex will be inner, which complex will be outer. You have to remember directly, and it will be rectified in the crystal field theory. So it has so many drawbacks, this complex. What is the first drawback of the Valence Bond theory? No clear-cut idea regarding the which complex will be inner, which complex will be outer. Why this complex inner, which complex will be outer? This is one concept, and no quantitative calculation of the magnetic character. And there is no difference in nature of ligand. Which ligand is weak ligand, which ligand is strong ligand, why this particular ligand is strong, why the particular ligand is weak, it could not explain. So Valence Bond theory has some defect, some drawbacks, and these drawbacks of Valence Bond theory can be corrected by crystal field theory. Now in this Valence Bond theory, you have to make one table. In the table, you have to write the first one column that what are the complex, the formula of complex, and their hybridation and their magnetic character. You have to write this. For example, this tetrahedral is a square planar complex, and it is what? Diamagnetic, because having no electrons. And tetrachloridonickelate is tetrahedral, which is paramagnetic, because having 2 unpaired electrons. So we have to practice like this, and question also different types of question asking in the computer examination regarding the magnetic character, shape of the complex, hybridization of the complex, which is inner, which is outer. But the inner orbital, outer orbital complex, you have to remember this thing. Inner means that is low spin, inner means low spin, outer means high spin. I have to just, I will tell you one trick. Who remember who? That is who. One is who, another is sleep. These two words remember for your betterment. For your who means here, who means weak, high spin, outer orbital complex. Who means weak, high spin, outer orbital. High spin means outer. That means ligand is weak. Ligand is a weak ligand. You will read why the particular ligand is weak, why the particular ligand is strong, we will discuss in the crystal field theory. But remember, HO, high spin, outer. Li, low spin, inner. Low spin, inner, high spin, outer. And who, first remember who. Who means it is a weak ligand. Weak ligand, high spin, outer orbital complex. And strong ligand, low spin and inner orbital complex. So this is a very short form for your, you can remember this formula so that you can know which is inner, which is outer, which is high spin, which is low spin complex. Okay, this is regarding the formation of different types of complex and their shape and their structure and magnetic character. Okay, thank you all.